A jar contains 4 red marbles numbered 1 to 4 and 6 blue marbles numbered 1 to 6. If you draw one marble at random, what is the probability that you draw a red marble? So this is basic probability. So we'll use the basic probability formula. Probability of the event equals favorable outcomes divided by the total possible outcomes. So the probability of a red marble is the outcomes that are red marbles, there's 4 of them, divided by the total possible outcomes, which is 10 marbles. If we divide, we'll get to decimal 0.40, so multiplying that by 100% would give us a 40% chance of getting a red marble, which makes sense because there's 4 red marbles out of 10. What's the probability that we would not draw a red marble? Well, this is a complement probability, probability that the event does not occur. So the probability of not occurring would be 1 minus the probability that the event does occur. So the probability of not getting a red marble equals 1 minus the probability of getting a red marble, which was 4 out of 10. So if we simplify this, 1 minus 4 out of 10 would be 10 out of 10 minus 4 out of 10, which is 6 out of 10. So that equals 6 out of 10, which is 0.60 or 60% chance of getting a marble that's not a red marble, which makes sense because 6 of the marbles in the jar are not red, they're blue, right? So there's a 60% chance of getting that blue marble or not getting a red marble. Probability of drawing a blue and even marble. So this is still basic probability because we're just asking the question, what's the chance of getting a marble that's both blue and even? So it's still that probability of event formula. Favorable outcomes divided by total outcomes. So the probability of blue and even would be the outcomes of a marble that's blue and even. So there's 6 blue marbles numbered 1 through 6. So the even marbles would be numbered 2, 4, and 6. So there's 3 even blue marbles. So that's 3, which are blue and even, out of all the marbles. 10. And 3 divided by 10 is 0.30, which is, if we convert it to a percent, would be 30% chance of getting a marble that's blue and even. Makes sense. So there's a 60% chance of getting a blue marble, 30% chance of getting a blue and even marble, which makes sense because there's half as many of the blue marbles are even. Okay, what's the probability of drawing an even marble given that you know it will be a blue marble? Okay, so now this is a conditional probability question because of the given. Part. So given that we know the marble's blue, what's the probability that it is? We get an even marble. So it's the probability of A given B, and basically it's the outcomes that are both A and B divided by total B outcomes, total outcomes that are B. Total outcomes for B. So the probability of even, given that we know the marble is blue, this line here also means given. So it's basically the probability of even given blue equals outcomes that are both blue and even. So there were 3 even blue marbles. So 3 divided by total outcomes that are blue. So there's 6 blue marbles. So if we simplify this, is 3 is half of 6, so that's 0.5. Multiplying by 100%, we get 50% chance. If we know that the marble is going to be blue, and there's a 50% chance that it'll be even, which makes sense because half the blue marbles are even. What's the probability of drawing a blue or even marble? So this one is disjunctive probability now. And it's the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So the probability of blue or even is the probability of a blue marble, which would be 6 out of 10, plus the probability of an even marble. So we have to know how many even marbles are there. There are 3 blue even marbles, and there's 4 red marbles numbered 1 through 4. So the even red marbles are 2 and 4. So there's 2 even red marbles, 3 even blue marbles, a total of 5 even marbles out of 10, minus the probability of a marble that's both blue and even. Well, there were 3 blue even marbles out of 10. So simplifying, we have 11 minus 3 on the top is 8 out of 10. Simplifying that, we'd get 0.80, which multiplying by 100% is 80%. So there's an 80% chance of getting a blue or an even marble, which makes sense because it's 6 blue marbles and then 2 reds that are even. So that's 8 possibilities out of 10, 80% chance. So these are all examples of outcomes for drawing one marble, if you draw one marble. But what if we are drawing 2 marbles from the jar? Now what happens? So if you draw 2 marbles at random and replace the first marble to the jar, replace the first marble, before drawing the second marble, what is the probability that you draw a red marble first and a blue marble second? So this is an example of independent events. This type of problem is probability of independent events. And they're independent because we replace the first marble, making it so that the second marble's outcome does not depend on the first marble. Okay, if we take a marble out, we put it back, we take another marble out, that second marble's outcome doesn't depend on the first marble's outcome because we put that first marble back. So these are independent events. So then the probability of A and B occurring is the probability of A times the probability of B. Independent events. So the probability of a red first and blue second equals the probability of a red marble, which was 4 out of 10, times the probability of a blue marble, which was 6 out of 10. So that's 24 out of 100, which simplifies to 24% probability that you'll get red first and blue second if the events are independent. So we're getting down to smaller chances. When we take 2 marbles, we're trying to figure out the probability with 2 marbles versus just 1 with a certain outcome. If you draw 2 marbles without replacing, so we replaced in the first one, but what happens if we do it without replacing? The first marble, if we do it without replacing that first marble before drawing the second marble, what's the probability that we draw a red marble first and a blue marble second? So it's the same question. The only difference is now we're not going to put the first marble back before we take the second marble out. So now the events are no longer independent. They're dependent events because we don't put the first marble back. So if we don't put the first marble back, the outcome of the second marble depends on the outcome of the first marble. So it's the probability of A and B again, but it's the probability of B second given A first. Probability of blue second given red first would equal the probability of a red marble first, which is 4 out of 10, times the probability of a blue marble. There's 6 blue marbles, but it's now out of 9 marbles because we kept the first marble. So what happens is the total goes down when we keep that first marble. So this would be 24 out of 90, which corresponds to 26.7% chance that this will occur. If we draw 2 marbles without replacing the first marble before drawing the second marble, what is the probability that we draw a red marble first and a red marble second? So the only difference here now in this question is that we want to know the probability of drawing 2 red marbles instead of a red first and a blue second. So it's dependent events again because we did not replace the first marble. And it's the probability of A and B, where the probability of B second given A first. So probability of a red second given red first equals 4 red marbles out of 10 for the first marble, and then only 3 red marbles remaining out of 9 for the second marble. Simplify this, we get 12 times 90, or sorry, 12 divided by 90, which becomes 13.3% chance. Smaller chance because there's only 3 red marbles remaining in the jar if we keep that first red marble. So these are probabilities for 2 marbles. What if we want to know about possible combinations and think of it as a counting probability? Counting and a counting probability. If we draw 2 marbles and the first marble is red, how many possible combinations are there for the 2 marbles? So this is just a counting problem. It doesn't say anything about probability. It's just saying what are all the possible combinations. Counting and possible combinations or total outcomes would be that counting principle, M times N. Outcomes for the first marble times the outcomes for the second marble. So the total outcomes equals 4 possible outcomes for a red marble first, because there's 4 red marbles. Assuming that we do put that red marble back, then the outcome for the second marble, which doesn't have a condition on it, would be 10, because there's 10 marbles. So all possible outcomes with the red marble first, and assuming that we put that red marble back, is 40. If we didn't put the red marble back, then there would only be 9 possible outcomes for the second marble, and it would be 36. If we draw 2 marbles and do not return the first marble before drawing the second marble, so now we're not putting that marble back, what is the probability that both marbles are red? So this is, we can treat this as a counting probability question. So the probability of 2 reds would be all the possible combinations of 2 reds, and then divided by all possible combinations for 2 marbles. So the probability of 2 red, possible combinations for 2 red marbles. If we don't put the first marble back, there's 4 possibilities for the first marble, but only 3 for the second because we don't put the first one back. And then all possible combinations. If we don't put the first marble back, there's 10 possible combinations for the first marble and only 9 for the second because we don't put the first one back. So that gives us 12 divided by 90, which simplifies to 13.3%. And you might recognize this as being the same thing that we got when we found the probability of a red marble second given a red marble first. So that was also 13.3%. You can think of this as dependent events and solve it this way, or you can also think of it as a counting problem, where you have combinations for 2 red marbles divided by all combinations. They both lead to the same result.